Good morning, everyone, and welcome to today's Code Jam session by GDSC on dynamic programming. Before we start, I'll share my screen for the PPT. Hope the screen is visible. So, introducing myself, I am Hardik Pawar from 5th semester CSC RVCE, and today's topic that we are going to cover is dynamic programming and the various techniques involved in it. The table of contents for today's session being Introduction to DP, starting from the base level, the various DP techniques used to solve various competitive programming problems, which are memoization, tabulation, and space optimized tabulation. Nextly, the applications of DP in day-to-day problems, and some sample exercises from LeetCode and Coding Ninjas. So coming to the introduction of DP, when, where and how it can be applied. Firstly, to characterize a problem that can be solvable by DP, it can be classified into a DP problem if it satisfies the minimum two criteria. The first one being the optimal substructure, wherein the optimal solution for the main problem can be constructed and derived from the optimal solutions of its base problems. And these subproblems are again recursively divided into problems until and unless we reach a base case where the exact solution is known. Secondly, it helps us to manage time and recursive stack space by storing the answers for the overlapping subproblems in an in-memory cache. In DP, we'll get a lot of subproblems. When we keep dividing the problem into subproblems, we'll get many concurrent and same subproblems, the result for which can be stored in an in-memory cache, which is nothing but the DP array. So now let us take an example, a very simple example to brush up the concepts of DP if you already know about it, or an introduction to DP if you're a beginner. So a Fibonacci sequence is a sequence of numbers wherein the first number is 0 and the second number is 1. And the third number is the sum of the last and second last numbers. This can be formulated in a recurrence relation given over here. The nth term of a Fibonacci sequence is the summation of the previous and this term two times behind in the series. Basically, Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci n minus 2, with the base case being Fibonacci of 0 is 0, Fibonacci of 1 is 1. This is basically a zero indexed ordering, that's why it's taken like this. Now suppose we want to compute Fibonacci of 5, we can visualize this using a recursive tree, which is shown over here. Computing Fibonacci of 5, we require the value of Fibonacci of 3 and Fibonacci of 4, and similarly so on and so forth till we reach the base cases. Note that here we can analyze how many function calls and how many basic operations are executed. The number of function calls will be equal to the number of nodes in the recursive tree, which in this case is 15. So we can conclude 15 function calls are being executed, and similarly we can count the number of parent nodes to see how many additions are taking place, which in this case is 7 additions. For a small n value, this is not a significant increase in space and time, but for bigger problems this can be redundant. As you can see, there are subtrees which are again calculated. Like Fibonacci of 3 is over here, left child of Fibonacci of 5, and again Fibonacci 3 subtree is repeated over here. So now let's try and analyze the space and time cost reduction if we use the tabulation approach of DP, which is the iterative bottom-up approach to solve a problem. We store the base case solutions in the DP array, Fibonacci of 0 being 0, 1 being 1. Similarly, when we compute Fibonacci of 5, we first go to Fibonacci, just bottom up, sorry. Then we compute Fibonacci of 2, the number being 1 more than the previous one, which is Fibonacci 1 and 0, which is already stored in the DP array, being 0 plus 1, 1. Similarly, then we compute Fibonacci of 3, which according to the recurrence relation is Fibonacci of 2 and 1, 1 being already stored in the DP array, and Fibonacci 2 has already been calculated in the previous step and stored in the cache, the DP array. And similarly, Fibonacci of 4, Fibonacci of 5, the final answer is computed. Notice over here the red tick marks highlight the function calls, and which in this case being only 1, and the number of basic operations executed is 4, which is the number of additions. So you can see there's a dramatic reduction. Almost 1/4 of the function calls are reduced to 1/4, and additions are reduced to almost half. even for a small n value. So you can imagine the savings for a big n value. So the observation that we can conclude by the advantage of DP over divide and conquer being that it offers significant reduction in CPU time and function call overhead in the stack space, along with a decrease in the number of basic operations that are to be performed. This not only makes the process of algorithm execution more streamlined, it also enhances the computational efficiency of the algorithm. So yeah, let's go to the next topic, which is being the various DP techniques that can be applied to a problem. First one being memoization, which is a top-down approach. The direction of problem solving is from the main problem to sub-problem. This is a recursive formulation and it typically uses a helper function to fill the DP array. Next approach is tabulation, which is an iterative approach, and the direction of filling is from the sub-problems to the main problem in a bottom-up fashion. The advantage of this over memoization is that it's easier to understand, the code size is less, and it does not use a recursive stack space since it is iterative. The next one is a space optimized tabulation, which is exactly similar to the tabulation approach, but it uses space more efficiently, which we'll get to know in the future, in the subsequent slides in the example. So here's the C++ code for the Fibonacci sequence for the memoization approach. At the bottom over here is the main function, which initializes the DP array to have n plus 1 elements. All are initially initialized to -1. -1 being a placeholder that the value is not yet computed for that index. So if you take any index I in the DP array, its value is equal to the Fibonacci of the ith term. Fun over here is a helper function which helps us in filling the DP array from top to bottom, from the sub-problem to sub-problem direction. So let us discuss the helper function, which is a recursive function. And any recursive function has two main components, base case and recursive case. So the base case here being that if n is 0 or 1, denoted by n less than equal to 1, we directly return the number. As we had seen before, Fibonacci of 0 is 0, Fibonacci of 1 is 1. Next up, if n is more than 1, we first do a lookup in the DP cache to see if that value for that particular index has already been computed. If it has been, we directly return the value that was stored in the cache. In case the value is not computed, we first compute the value by finding the Fibonacci sequence for the n-1th and n-2th term, computing that result and storing it in the cache, and then returning that to the calling function in the recursive stack space. So in this way, the DP array is filled from top-down approach, the direction being main problem to sub-problem. If you look at the time complexity in this, it is linear, order of O(n), and the space required is order of n plus order of n, where DP array and recursion stack space take up linear space. Next up, let us discuss the tabulation approach for the same problem. We again initialize the DP array having n plus 1 elements, all initially initialized to -1. DP of 0 equal to 0 and DP of 1 equal to 1 are the base cases for the 0th and 1th term. The problem of direction filling of the DP array is from sub-problem to main problem. So we run a for loop from the 2th index to the nth index, increasing by 1 for each iteration. And DP of I being the Fibonacci of the ith term, which is itself dependent on the summation of the I-1th and I-2th term. The final answer will be stored in the last index of the DP array, which is DP of n, and that is returned as the final answer. Here you can notice that the space and time complexity is same, except that for space, the additional recursive stack head overhead is reduced. Now coming to the third approach, which is the space optimization for the tabulation approach. It's very similar to tabulation, but it reduces the need for DP array and takes up only constant space. So how is this done? Initially we check if the base case is satisfied, whether user is asking for 0 or first term, and return that directly. Then we initialize the first and second term. First being, let's suppose there is the ith term. First pointing to 2 terms before the ith term, and the second variable pointing to 1 term before the ith term. And the third variable stores the summation of the first and second variables. So again we run the for loop from 2 to n, n being the number we want to find the Fibonacci sequence of. The third term, that is the ith term, will be the summation of the last 2 terms, and then we update the first term to the second term to the third term. Basically the I minus 2th term becomes the I minus 1th term, and the I minus 1th term becomes the recently computed term. After this calculation is done, we can return the second term, or we can even return the third term, because at the end of the loop both have the same value. And if you have any doubts, feel free to text it in the chat box. After like each slide topic, I'll be looking at the chat box for any doubts. So coming to the applications of DP, the first and foremost and the most important application being to reduce TLE errors in lead code and any competitive programming challenges that you do. If you've experienced some competitive events, you know that this is a very frustrating error, and DP can help excessively in reducing this. Secondly, it's mainly used in many grid problems, such as shortest sum problems, shortest triangle sum problems, etc. And it is majorly used in many optimization problems. Find the minimum sum, maximize profit, etc. One of them being 0-1 knapsack, as you would have studied in your design and analysis of algorithms course. So now let us take some exercises from some DP exercises and try to solve them. So the first exercise is called frog jump, which is a one-dimensional dynamic programming question. The input parameters that we are given is the number of stairs and a frog. The objective is that the frog wants to climb from the 0th stair to the last stair, which is n-1 stair. And the constraint is that the frog can climb either 1 or 2 steps from the current stair. We are also given a height array which is used for the energy calculation. So whenever a frog jumps from the ith stair to the jth stair, the energy consumed is equal to the absolute difference of the height value at those corresponding indexes, which is highlighted over here. So our objective function is that we have to minimize the energy that the frog uses to jump from the 0th stair to the n-1 stair. Now let us come to the intuition and approach and see what keywords are there in the problem that can help us to solve it. So it is an optimization problem which can be understood from the keyword minimum energy that is required to go from the first stair to the last stair. We can also observe that there is optimal structure and overlapping subproblems criteria getting satisfied, as the current stair can be reached from 1 stair before or 2 stairs before. So we can classify this as a DP problem. So let us come to the 3 approaches that can be used to solve this. First one being memoization. This is not the complete solution. This is just the main function which initializes the DP array and then calls the helper function to fill the DP array. The DP array is from 0 to n-1, which is the index. Any index I in the DP of array in the DP array denotes the minimum energy required to that stair. Suppose DP of 4, that's the minimum energy that is used to reach the 4th stair from the 0th stair. After this, we call the helper function, which accepts 3 arguments: the index, current index at which stair you are, the height array, and the DP array. So again, coming to recursive function, there are 2 cases: base case and recursive case. The base case being if you are at the 0th stair, the energy required to reach the 0th stair from the 0th stair will be 0. That's why we are returning 0 over here. Next up, we do the lookup in the cache to see if the value to reach the current stair has already been computed. And if it has, that is, it's not equal to -1, we return the energy to reach that stair, minimum energy. Next up, we do recursive case, in which there are again 2 possibilities. The current stair can have reached from 1 stair before, because the frog can jump 1 or 2 steps. So the direction of filling is top to bottom. So we are going in somewhat of a backward direction. So the energy to reach current stair, the 2 possibilities, suppose the current stair was reached from 1 stair before. We are calculating that energy over here, which is basically the absolute difference of the height values at the current index minus the height value of the previous index, plus, this is important, plus the energy required to reach the I-1 stair. Suppose you are at the 4th stair, you have reached 4th stair from the 3rd stair, that is, the jump is 1. So you would have taken the energy as height of 4 minus height of 3 absolute, plus the energy that was required to reach the 3rd stair. So like this, we keep going back to the base case. The second possibility of the recursive case being that the current stair could have been reached from 2 stairs before. So initially what we do is we initialize the second variable as int max, and I'll tell you why. We do int greater than equal to 2 to check if it was a valid index. Suppose you're at the stair with the index 1, and if you go 2 steps behind, you'll reach -1, which is not a valid stair, it doesn't exist. So in that case, the default value of the jump to variable will be int max. I'll explain later why we took int max. Now suppose if it's a valid index, let's say 3, you can reach stair number 3 from stair number 1, so it is a valid case. Similarly, we compute the energy to reach that stair from 2 stairs before, and the energy that was required to reach the i-2th stair. After we find the energy values for reaching the current stair from 1 stair before and 2 stairs before, denoted by jump 1 and jump 2, we store the minimum of those values. Since we're calculating the minimum energy, store it in the cache and return it. Now suppose we are at the first stair, we can only calculate jump 1 because we can reach first stair from the 0th stair. Jump 2 will be int max only, this whole block won't get executed. So minimum of jump 1, which is, let's say for example 10, comma int max, will always select jump 1. So that's the use of int max over here. Yeah, let's go to the tabulation approach for the same problem. We again initialize the same DP array having n elements, n indexes, 0 to n-1, initially initialized to -1. The base case being highlighted over here. In recursion, in memorization, it was over here. In tabulation, it's equivalently converted over here. DP of 0 being 0, energy required to 0th stair being 0. Then we fill the DP array from the first index to the n-1th index, which is given by this for loop. And the jump 1 and jump 2 calculations are the exact same as the memorization approach. Jump 1 being energy required to reach from 1 stair before, jump 2 being energy required to reach from 2 stairs before. We store the minimum value of each of these jumps, whichever is minimum, in the DP of I array, which is the minimum energy required to reach that ith stair. After this has been filled, the final answer will be located at the last index of the DP array, since we want to reach the last stair. So finally, the answer that we return is DP of n-1. Now, space optimizing the previous approach, we don't need to actually use a DP array. We can just use two variables, first and second, if you recall, the same as the somewhat same like the Fibonacci series. So this takes constant space, and we maintain two variables, first and second. Second variable holds the i-1th energy, the energy required to reach the i-1 stair. First variable holds the energy required to the i-2th stair. So I'll explain that using this for loop, same for loop, 1 to n-1. Energy required to reach the current stair from one step before is the absolute difference of the height at the corresponding indexes plus the energy required to reach the second stair, i-1th stair. And jump 2 being the same int max default value, and the total energy being the difference in heights, absolute difference of the heights, plus energy required to reach the i-2th stair. First, second, third, you can think of it like that. So in the next iteration, we move one step forward. So we convert the i-2th term to i-1th term, which is denoted by first equal to second, and then the second term is equal to the third term. As you remember in Fibonacci series, the third term being the minimum energy of jump 1 and jump 2. We could have introduced a third variable also here for better clarity, but this code reduction seems more readable and easier to understand. After this has been computed, the final answer will be stored in the second term, which is the energy required to reach the n-1 stair, and the successful answer will be retrieved. So now next, coming to a very popular lead code question called house robber. Again, this is a one-dimensional DP question, and the problem statement scenario given is such that there's a thief who wants to rob money in a street. The houses in the street are arranged in a circular manner. The normal variation of this you would have encountered is that they're arranged in a linear manner, but a circular manner adds another twist to the problem, which I'll say later. So when it's arranged in a circular manner, the first and last house are adjacent to each other, obviously since it's in a circular shape. The constraint is such that the security system in the houses is arranged such that if adjacent houses are robbed, the police will get notified. So what the thief wants to do now is he wants to return the maximum amount. He wants to steal the maximum amount of money that he can steal without alerting the police. So the problem we are given an integer array which represents the money at each house. So again, here are some keywords that tell that it's a DP problem. One being the max amount of money, some constraint, and overlapping sub-problems. So coming to the approach, this is very similar to the this is similar to another question, which is finding the maximum sum of non-adjacent elements in an array. This problem internally uses the maximum sum of non-adjacent elements problem, which I'll explain now. So firstly, the first and last houses are adjacent to each other. So if we rob the first house, we can't rob the last house and vice versa. So what we have to do is we have to make two reduced arrays. The first one not containing the last house, the second one not containing the first house, which represents the two cases, either first house is robbed or second house is robbed, etc. So then we have to use that helper function, that internal problem, to find the maximum sum of non-adjacent elements of both these two reduced arrays separately, and then whichever has the maximum value of money, that is returned as the final answer. So yeah, I'll only discuss the tabulation approach for this since it's a bit lengthy, not that much, but yeah. So this is the main function that is used. We are given n number of houses and the array which is which gives us the money at the ith house. So now the base case is if it's only one house, we can just return that house's value. Since it's not adjacent to any, we can successfully rob that house. Now suppose there are more than one houses. We have to reduce the arrays into two. The first array contains all elements except the last element, and the second array contains all houses except the first house, which is denoted by these statements. arr.begin returns the read-write iterator to the first index, and arr.end returns the read-write iterator to the last index. -1 being to go to the 0 to n minus 2th element. Then we individually compute the maximum value that can be stolen from these two reduced houses, which is stored in answer 1 and answer 2 for arr1 and arr2 respectively. And then finally we return the maximum value of these two answers. Now coming to the implementation of this maximum sum non-adjacent function, it is over here. Again, I could have divided this into three techniques: memoization, tabulation, and space optimization. But for simplicity's sake and not redundantly repeating it, I'll just do the tabulation approach. So this is the helper function to find the maximum for non-adjacent elements. We initialize a DP array for all the indexes 0 to n minus 1, initially with -1. We highlight the base case, that is there's only one house, the 0th index house, with that house's value itself, because if there's only one house, we can rob only that house. So initialize with arr0 being the money that is stored in the 0th house. Then we fill the dpth array from the index for the 1th house to the n minus 1th house over here. Now at each house we have two options, pick and not pick. If in case we don't pick the house, let's suppose we are at the 4th house and we don't pick it, the maximum value that we'll have is the maximum value we have had till the 3rd house. So that's why we retrieve the value for the immediately before house. Now in case we pick this house, that means the previous house, of course we cannot pick it because it is adjacent. So initially we store the default value of the house, the default value being the money in the current house, and in case it is a valid index, which I had told in the frog jump, it's similar to the frog jump. If the previous two houses is a valid index, then only add the maximum value that you had accumulated till the two houses before. So the first case being you cannot pick the current house, so the not pick value will be maximum value till before house. Second case being you can pick it, and if it is valid, the value being the value of the current house plus the maximum money you had accumulated till two houses before. And since this is a maximization problem, you have to pick the maximum value of money you get from either pick or non-pick cases store it for the ith house, and then fill the table accordingly. So the DP of ith index gives the value of maximum money you can accumulate till that ith house. So naturally, the last house being n minus the last, to complete the filling direction, the final answer will be stored in the n minus 1th index, and that is stored in DP n minus 1, and that is returned as the final answer, which is given as answer 1 and answer 2 for ARR1 and ARR2 respectively. And the maximum of these is the final answer, as I had said before. Yeah. Now next up, let us upgrade our problems, and let's jump to a two-dimensional grid problem which uses DP. So the given problem domain is such that we are given two values m and n, which represent a m cross n matrix. What we have to do is we have to find the total unique paths from the top left cell to the rightmost cell, which is denoted by the coordinates matrix 0, 0 and m minus 1 and n minus 1. And the given constraint is such that we can only move in two directions from the current cell, which is either bottom or right, that is either south or east. So the approach that we can use to solve this problem is firstly initialize a 2D DP array which mimics the input grid of m cross n dimensions. Each cell in the DP, let's say the ith row and jth column, that is DP ij cell, represents the total unique paths from origin 0, 0 to that coordinate, that is I, j. So the dependency direction for any cell is up and left. Since we are allowed to move in only two directions, bottom and right, the current cell could have been reached from, we are allowed to move bottom and right, the current cell could have been reached from either up or left directions, that is north or west. So that is the dependency direction. So firstly, let's discuss the memoization approach. This is the main function which initializes the DP array of m cross n dimensions, all cells being -1 initially. Then we use a helper function to fill the DP array. m minus 1, n minus 1 being coordinates for the goal state, the final bottom right cell, and DP being the DP array. So this is the actual helper function that calculates the DP ij array, fills the array. Again, there are two cases, base cases, recursive cases. Base case, if we are at the origin, if we are finding the unique paths from the origin to origin itself, that is I and j both are 0, then we return 1, since there's only one path from origin to origin. Now in case, I'll explain this out of bounds case later. It will make it clearer if I explain the recursive cases. Next up, we look up in the DP cache. If the value is computed, return that value. Next up, coming to the recursive case, the current cell could have been reached from either up or left. Now in case it was reached from up, we find the number of unique paths to reach that upper cell, which is given by I minus 1 j. Suppose this is ij, I minus 1 being the immediate cell above, that is one row above. Similarly, we find the number of unique paths from the left cell, from the current cell, the left cell. How many unique paths are there for the left cell, which is given by I, j minus 1. J being the current column, j minus 1 being the immediate previous column, that is the left column. So the number of unique paths to reach that current cell is equal to the summation of the number of unique paths to reach the upper cell plus the number of unique paths to reach the left cell. And that is stored in the ijth index for the current DP matrix in the cache and then returned. So here you have noticed that in case you are at the 0th row or the 0th column, if you do I minus 1, you will reach a negative index which is not valid, -1 and minus 1, yeah. So this base case is used to handle that out of bounds. In case you traverse outside the grid, you just return 0. There's an alternative way such that this base case can be removed and this if checking can be performed within the recursive case, which I'll highlight in the tabulation approach. Yeah, so coming to the tabulation approach, we'll fill the same methodology as the memoization, except that this is filling the DP array in bottom up fashion. So again, the same DP array, we initialize m cross n dimensions and initially fill it with 0, even -1 is fine. These two nested for loops traverse the matrix. The outer one traverses each row and this one traverses each column. So inside this, we're traversing each cell. 0 to m minus 1, 0 to n minus 1, and here is the base case. If we are at the origin, this happens only in the first iteration. If both I and j are 0, compute the number of paths to reach that origin cell from origin as 1 and continue. Skip all this recursion iterations. Again continue and go to the next cell. Now again, here you would have seen we are doing an if checking. Initially the number of ways to reach the upper cell is 0, and only if a row above the current row exists, then and only then calculate the number of ways to reach the cell immediately above the current cell, which is given over here. Similarly left, if we are in the first 0th column, there's nothing to the left of it, so initially the default value is 0. But suppose we are in any column greater than 0, there is a valid left column, and we calculate the number of steps, number of unique paths for the cell immediately to the left of the current cell using this formulation, which is same that the I j minus 1, same coordinates that I had said before. And the number of paths to reach the current cell being the number of paths to reach the upper cell plus the number of paths to reach the left cell of the current cell. And the final answer is stored in the bottom right corner, which is the number of unique paths from origin to the bottom right corner, the coordinates being m minus 1, n minus 1 of the DP array, and that is returned. So yeah, with that we come to the end of the session, and if you have any doubts, I am happy to take them. Sumit asks, can be solved using pure mathematics, right, or to save space? You're right. Actually, there's a predefined formula to find number of unique paths for m cross n grid. I believe it is m plus n minus 2 c n minus 1. But the thing is, if someone doesn't knows this formula beforehand, then they will have to use some programming approach like dynamic programming to find it. But in case you know the mathematical formula, well and good. You can actually solve that in constant space, yeah, and even faster time. The time being the number of the time being the same time complexity to find the combinatorial the NCM function. Is there a method to identify if a problem is DP or greedy? Okay, yeah, this is a very interesting question. Normally, the way you can identify this is sometimes it's trial and error. Now, let's take example of frog jump. If you can assume a sample input array like 1, 2, 5, 10, etc., etc., anything, and then you do a dry run on paper by doing the greedy approach, and then you do a dry run using the DP approach. In most of the cases, you'll, according to the, actually it depends on the input. Sometimes the greedy might work, but it won't work for all instances. So if you do DP, you'll always get the right answer. And the thing is, when greedy does not work for many problems. When coming to competitive program solutions, DP is the more commonly used, but greedy can be used. We have to carefully look at the question. Suppose there is a question that says the maximum denominator question. Wait, let me show you. Alright, so this is my example question. I'll just summarize the question. We are giving two arrays, one being the greed array and one being the cookie size array. So what we have to do is we have to distribute the cookies among the children such that this condition is satisfied. The size of the cookie is greater than or equal to the grid, such that each child is content, and we have to return the maximum number of content children. So here you can clearly see that it's a greedy problem because wait, I'll explain. It is a greedy problem because it does not have actually an overlapping substructure, because the value that you give to the current child, it should be sorted in ascending order. I'll explain the code. We firstly sort the greed and satisfied arrays in ascending order, and then we assign the minimum maximum size of the cookie that can be assigned to the least greedy child, which is done through this while loop iteration. Initial I is the pointer for the grid, j is the pointer for the size. While both are valid indexes, if the current size of cookie, which is the jth cookie, satisfies the grid for the ith child, then we increment the number of content child and move to the next child, and we anyways move to the next cookie for each iteration. So this is one example of greedy. In dynamic, what happens is it's more like a long-term gain. In the short term, you might have to choose a less optimal solution for in the long term to get the more optimal solution. But I think the main selection criterion to identify as DP or greedy is practice until you intuitively get to know it. Okay, thanks. So the PPT session has come to an end. If you have any doubts or anything that you want to talk about, I am open to take that. What about 3D DP? Next session. Yeah, actually there's dynamic programming 1 and dynamic programming 2 sessions. Today I had taken dynamic programming 1. So yeah, 3D DP and other problems will be covered in the next session. So mostly that won't cover the basics like memoization, tabulation, space optimization. We'll directly do mostly problem solving session there. The reason I didn't use any whiteboard or anything to do a rough draft of the problem was because I felt the code, if you look at the code visually, that is more easier to understand than the pen on paper approach, is what I felt. Like the code being very self-explanatory. Actually, many stock buy sell problems also come in 3D DP, so that can be covered in next session. Yeah. I stopped screen sharing because it was just going in an infinite loop. I joined late, so I don't know if you talked about this. Do we expect us to keep the space optimization? Actually, up to tabulation is very much fine. Space optimization, actually, it's even very difficult, somewhat difficult to understand and not that intuitive. So for the unique paths problem that I had recently covered, the 2D DP problem, it also has a space optimization version as well. But that was very kind of confusing to understand. It works. It was not that intuitive to understand, and what you cannot understand, you cannot explain also properly to the interviewer. So yeah, up to tabulation is fine. So if you have any more doubts that you couldn't convey in the session, you can feel free to reach out to me on WhatsApp, Instagram, anything to convey any doubts or just like any general query. So I'll wait for like another 2-3 minutes. If no doubts, then I think we can close the session.
Okay, so if none of you have any questions, then I think we can break for today. Thank you to Hardik for giving this informative session. I hope it was useful for all the attendees who came and attended this session. Next week or the week after that, we're going to have the second part of dynamic programming. Like he mentioned, we'll cover more advanced topic in this domain itself. So make sure to attend that session if you want to gain some knowledge about these concepts related to dynamic programming and how they're involved in solving various problems. So similar to this session, we'll be speaking about the concepts first, and then we'll slowly move on to the different problems on various coding platforms, and then how we actually use dynamic programming to solve them in a much more efficient way compared to the normal, let's say, brute force algorithms or whichever more simpler algorithms that we use. So once again, thank you for attending this session and enjoy your weekend.
Thank you, Prabha, for hosting this, and to the audience as well for the interactive chat. And yeah, hope you all had a great time. Bye.